Hello and welcome to the last video lecture of 2020, and we'll see how it goes. It's not too complicated. Today we're talking about acids and bases, and specifically we're talking about the pH scale of acids and bases. So let's dig right in. The pH scale is a way that chemists use to decide whether or not something is an acid or a base, or more specifically, how caustic, that is, reactive or damaging, an acid and a base is. All acids have a pH that is 7 or less, more specifically that is less than 7, so like 6.9 and lower. And bases tend to have a pH that is greater than 7, so 7.1 and greater, and substances that are neutral are considered to have a pH of 7. Now, so what does pH mean? Well, pH comes from a French term that means hydrogen power. So pH means hydrogen power. Like I said, it comes from a French term that means hydrogen power. But what it really is talking about in terms of a definition is it's talking about how much dissolved hydrogen is in a solution. Okay, so what that means is that if something has a lot of hydrogen dissolved in solution, it will create more H3O plus, something we talked about with neutralization reactions last week. So the hydronium ion. So we'll create more H3O plus in solution, and the more H3O plus in solution that a substance has, the more acidic it is. So that's what pH is. Now, a basic solution doesn't mean that there's no hydrogen in it, it just means that there's significantly less. And really, pH is a ratio of hydrogen, of dissolved hydrogen to hydroxide, OH. So that's really what we're looking at here. And so looking at this pH scale that's presented to us, we see that pure water would be something that we would be talking about when we talk about pH of 7. Your acids are things like milk, coffee, and tomato juice, apple juice, lemon juice, and gastric acid, which is the hydrochloric acid that's in your stomach. Things that are basic can be eggs or baking soda or soap or ammonia solution or bleach or concentrated solutions of alkalis like sodium hydroxide or like I said, ammonia or let's see, yeah. So those are our stronger bases. Now, like we said, the pH of acids are substances with a pH that is less than 7. And the closer pH gets to 0, the higher H3O plus concentrations, or the more acidic a substance can be. So if I said that I had a scale of 1, 2, 3, 4, 5, 6, 7, right? If I drew sort of a representation of that, I would say that I'd have significantly large amounts of H3O plus in my acids, and then on the bottom side of this little picture I would have OH minus. So with these super strong acids like the acids of the pH of 1 or 2, there's a lot of H3O plus and very little OH minus. So the closer we get to 0, the larger the amount of H3O plus is. Now, the pH of acids also talks about them logarithmically, and we're not going to do those calculations today. But what we can do is that we can see the fact that how much hydrogen is dissolved versus the concentration versus the type of acid. So, like for example, stomach acid, which is a very, very strong acid, has 0.1 hydrogen concentration, H3O plus concentration, and that's actually pretty strong stuff. But things like black coffee is 1 times 10 to the, looks like minus 3 maybe, is not that bad. So if you spill something considered to be stomach acid on your hand, you might get a chemical burn. But if you spill black coffee on your hand, that's not too hot, nothing will happen. So it's the degree of reactivity. Battery acid, which has a pH of 0, is sulfuric acid. It's actually it's really strong, and it'll eat right through clothing. It'll give you a chemical burn if it's not diluted right away. So these are things that we need to consider. Now, we're not going to do these calculations, but the common calculation for pH is equal to the negative log of the concentration of H3O plus. So what that means is that if I wanted to find the pH of, say, I don't know, tomato juice, I would take the negative log and times the concentration of tomato juice, which is 1 times 10 to the minus 4. So in this case, when I would plug this into my calculator, I would get a pH of 4. So that's kind of how some of the calculations for pH would work. And again, we're not going to do those in class this year, but I'm just making you aware that that's a very simple calculation you can use your calculator for. Now, bases are substances with a pH that is bigger than 7, and the closer the pH gets to 17, the greater the OH minus concentration of the base is in solution. So to continue the diagram from before, 7, 8, 9, 10, 12, 13, 14, you would see something like this. This would be your OH minus concentration, and then this would be your H3O plus concentration. And so what I'm getting at here again is that as you are becoming, as a substance is becoming more and more basic, or you're comparing substances that are more and more basic, the ratio of H3O plus to OH minus is largely in OH minus's favor. So if I were to continue and actually complete the actual diagram, so if I was to draw this actual diagram out, it would look something like this. And what I'm trying to illustrate here is the fact or the idea that, the ratio or relationship of hydroxide to H3O plus. So, as things are, this would be neutral. So at a pH of 7, we'd be talking about neutral. So we would be saying that we would have equal amounts of H3O plus and OH minus. My drawing might not represent that. And then, so that's something that's important to understand, so that if the concentration of H3O plus is equal to the concentration of OH minus, then we would say the substance is neutral. If the concentration of H3O plus is greater than the concentration of OH minus, we would say the substance is acidic. And if we would say that the concentration of H3O plus is less than the concentration of OH minus, we would say that the solution is basic. Now, if this was the year where we were giving a final exam on this, I would tell you to memorize this relationship right here. And this picture is basically doing a good job to represent that. So again, bases are substances that have pH greater than 14 and they have a higher OH minus concentration than H3O plus concentration, and that's what makes them basic. Going back to the pH of bases, again, we're looking at some substances here like Drano and bleach and ammonia cleaner and regular soap, and these things are all sort of they're sort of really basic solutions, and some of them are basically benign like seawater, or you can put some baking soda on your hand and it won't do anything, but if you get like drain cleaner on your hand, you might end up with a pretty nasty chemical burn, so we try to avoid that. So if I wanted to calculate the pH of a base, what I would do is I would take the pH, or not the pH, I would take something called the pOH, which is equal to the negative log of the concentration of OH minus. And so I would say that if I wanted to calculate, say, the pOH of, let's say, soap, let's say baking soda. Okay, so if I want to do baking soda, I would take the negative log of 1 times 10 to the minus 5. And I would get something I would get a pH value of 5. Now, but if I really wanted to figure out the pH, I would take the idea that the pH plus the pOH has to be equal to 14. So what I would do then is I would take pH plus 5, which would equal 14. I would then subtract the 5 to the other side and find out that the pH of this solution is equal to 9. So the pH is always describing how much hydrogen is dissolved in solution. It's not really how much the pH is always describing how much hydrogen is in solution, the relationship. So the lower the pH, the more hydrogen is dissolved in solution. The bigger the pH, the less hydrogen is dissolved in solution. And that's basically all that we need you to know about acids and bases. And so once you're done with this, there is a survey I'd like you to complete. And that wraps up the knowledge that you need to know about the content for chemistry for this year. And I will be reaching out to you at the end of this week to just touch base and make sure you guys have a good summer. So we'll talk later.